Okay, so before we start, as you're probably aware, exam number 3 starts on Friday, covering chapters 9 through 11. That'll be Friday through Monday. So that means that Thursday evening from 7 to 8, we'll have an online Zoom question and answer session. We'll be filming the review tomorrow afternoon. So by tomorrow evening, we should have the exam 3 review posted. So that gives you about 2 days to take a look at that review and come up with a list of questions and come with those questions Thursday at 7. So today we're going to review what we learned about halohydrons on Friday. And then after we do that, we have one more addition reaction from chapter 10 to learn, the hydroboration oxidation. And then we'll start chapter 11 with the introduction to alkynes. So the last thing that we learned at the end of class on Friday was related to the regioselectivity of the halohydron formation. We said that the more substituted alcohol is formed, meaning that water attacks the more substituted carbon of the bromonium ion as opposed to the less substituted carbon of the bromonium ion. And the explanation we gave is summarized here on the board. So our bromonium ion has a positive charge, or it's a halonium ion if we consider that it can be a bromine or a chlorine, depending on which halogen we used. So our halonium ion is very similar to a protonated epoxide because it's a 3-membered ring with a positive charge on one of the atoms in that ring. And so when a 3-membered ring with a positively charged atom undergoes a ring opening, the bond breaking is more advanced than the bond making at the transition state. And so that leaves us with a partial positive charge at the carbon that is being attacked. And we know that that partial positive charge is going to be more stable on the more substituted carbon. So when we compare the two possible transition states for this reaction, we see that the one with the partial positive charge on the more substituted carbon will be lower in energy and will therefore lead to the major product that is observed. Okay, so we will obtain the more substituted alcohol from a halohydron reaction because, like the acid-promoted epoxide ring opening, the bond breaking is more advanced. In this case, it's a carbon-halogen bond breaking is more advanced than the new bond, the carbon-oxygen bond that is being formed. Any questions about that? Okay. So we have here then a table summarizing what we learned about forming halohydrons. The mechanism, bridged halonium ion, no rearrangement, anti-addition, more substituted alcohol is formed, therefore giving us the less substituted halide. And all of those details follow from an understanding of the mechanism. So we want to make sure that we have a good understanding of this mechanism, which is very similar to the halogenation mechanism with an SN 1.5 step, similar to the epoxide ring opening thrown in. So why are halohydrons important? Well, it goes back to something we learned in chapter 9, which is that halohydrons, vicinal halohydrons, are the precursors to epoxides. Ethers in general are formed by Williamson ether reactions, and an epoxide is formed by an intramolecular Williamson ether reaction, where we have our OH and our halide on consecutive or adjacent carbons. So we start with an alkene, convert that into a vicinal halohydron. You see we get the more substituted alcohol as we would expect. It doesn't matter which base we use. We can use a less hindered base, a more hindered base. It doesn't matter at all because when a base encounters this molecule, it's going to deprotonate the OH much faster than it would perform a substitution or an elimination. Because acid-base, when you're talking about intermolecular processes involving two molecules colliding, acid-base reactions are faster than anything else because we're just transferring our smallest nucleus, a proton, from one heteroatom to another. So hydroxide or any other alkoxide base would deprotonate that alcohol, cause the intramolecular Williamson ether reaction to occur, and generate the desired epoxide. Okay, so two-step process, alkene to vicinal halohydrin, vicinal halohydrin to epoxide. That's what you want to use anytime you need to synthesize an epoxide. Any questions? All right, so earlier on in the chapter, we learned that if we react an alkene with water and sulfuric acid, we generate an alcohol. But because of the mechanism, Markovnikov's rule, we end up forming the more substituted alcohol. What if that's not what we want? What if we want the less substituted alcohol instead? Fortunately, there was a chemist at Purdue University named H.C. Brown. He solved this problem back in the 1950s when he developed a process known as hydroboration oxidation. It's a two-step process. So each of these reactions is a separate step. And the hydroboration is the addition reaction. So that's the one we're going to focus most of our attention on in this class, in this chapter. So we take an alkene. We react that alkene with borane or BH3. So this is our hydroboration step. So what happens in this reaction is we add a hydrogen to one carbon, and we add BH2 to the other carbon of our alkene. Okay. And then we add hydrogen peroxide and a base, a hydroxide base. And then that is our oxidation step. The oxidation is also a substitution because we replace the carbon-boron bond with a carbon-oxygen bond. Okay. So we're not directly adding water across the double bond, but that's the net result. We're adding hydrogen and BH2 across the double bond, and then we're converting BH2 into a hydroxy group. Okay. So again, we'll focus on the hydroboration step. We'll just talk a little bit about the oxidation step. This is a very important reaction in organic synthesis. As I mentioned, developed in the 1950s. It was so widely used that Professor Brown won the Nobel Prize in 1979 for his discovery of this reaction. There's an interesting story behind its discovery that I'll just mention briefly to you. So Professor Brown came from a humble upbringing. He was the child of immigrants from Eastern Europe. He graduated from college in Chicago during the Depression in the 1930s. So money was tight, but he had a girlfriend at the time, and she wanted to get him a graduation present when he graduated from college. And she didn't have a lot of money either, but she was a chemist, and she knew that he liked books. And so she went to the university bookstore there at the University of Chicago, and she found a book that fit in her budget, and that book was entitled The Hydrides of Boron and Silicon. Now, if you look at the structure of BH3, you could consider BH3 as a hydride of boron. Okay? So this might not seem like a very romantic gift, but it worked very well for the Browns. They ended up getting married, and they remained married for the rest of their lives. They both passed away in their 90s, probably about 5 years ago. So they were married for probably over 60 years, maybe up to 70 years. And this book that his girlfriend and then wife bought him actually launched his Nobel Prize winning research, because when he read that book, he came up with the idea of performing the hydroboration reaction. So when you're getting ready to graduate and people are asking you what you want for graduation, I might suggest that you ask for a chemistry book because you never know where that might lead. Okay. So in this case, it caused H.C. Brown to focus on BH3 and its chemistry. BH3 is known as borane. It's a very reactive molecule. It does not have the octet. There's only 6 electrons around that boron. And so it's very Lewis acidic. So much so that you can't store it. So when you're performing a hydroboration, you're actually not adding BH3 to the reaction mixture because BH3 can't be stored. You're adding something that is generating BH3. So you can dimerize the species and you generate something called diborane. We're not going to draw the Lewis structure for that because it's more confusing than it's worth, but just recognize that there is a stable dimeric form that when you dissolve it in solution can then dissociate and give you the BH3 that would then react with an alkene. You can also complex the Lewis acidic BH3 with a Lewis base, and the most common ones to use are ethers. So we can take BH3 and we can form a complex with THF, which we know is a very good polar aprotic solvent. It's also Lewis basic. And so we would draw the complex between BH3 and THF in this fashion. This boron-oxygen bond that we've drawn is much weaker than a typical sigma bond. There's going to be an equilibrium between the complex and the dissociated molecules. But most of it will be in the complex, which allows us to store it and have it be stable. But then when we dissolve it in solution, there's enough of the free BH3 that it can encounter an alkene and perform the hydroboration reaction. So sometimes when we're writing Lewis acid, Lewis base complexes, we just put a dot in between the two components. So when you see BH3.THF, that indicates this particular species. So when we're performing a hydroboration and we're writing down the reagents, we could either write BH3, B2H6, or BH3THF. Any of those would be acceptable. Even though we're not technically adding BH3, if you write that over the arrow, we'll know what you mean. Okay. So let's look at some data regarding hydroboration, the hydroboration step of the hydroboration oxidation. And the data will help us understand the mechanism of the reaction. So if we take a terminal alkene or any unsymmetrical alkene where we have a more substituted carbon and a less substituted carbon, the boron is going to end up on the less substituted carbon, okay? The hydrogen is on the more substituted carbon, and I actually chopped a carbon off my structure there. So remember, when you're drawing products on tests, always count your carbons because it's very easy to drop a carbon the way I just did. Okay. So we get the less substituted borane from this reaction. Okay. So with this particular alkene, if we perform a hydroboration, we know the boron is going to attach itself to the less substituted carbon, but there's also stereochemistry that we have to think about in this case. And it turns out that the hydrogen and the BH2 are going to be cis to each other in the product, okay? Is this product chiral? Okay, I see some heads nodding. Yes, it's chiral. So because the starting alkene and the BH3 are achiral, we know it's going to be formed as a racemic mixture. On an exam, I would expect you to draw them both. Here to save time, I'm just writing plus enantiomer. So since the boron and the hydrogen came from the same side of the alkene. What kind of addition is this? This is a syn addition. And it is only syn addition. So that tells us that the mechanism of hydroboration must be different from the mechanisms of the other addition reactions we've learned in this chapter. The hydration and the hydrohalogenation both gave syn and anti-addition. The halogenation and the halohydrin formation gave anti-addition only, and the hydroboration now is giving us syn addition only. So this is the only one that gives us exclusively syn addition. So the mechanism must be different than the mechanisms of the other addition reactions we've learned in this chapter. So in addition to the information here, there are no rearrangements in a hydroboration reaction. So with no rearrangements and only syn addition, what kind of intermediate do we know is not forming? Yeah, we know we're not forming a carbocation. We also know we're not forming some sort of a bridged three-membered ring species because that would give us anti-addition. So we need a new reaction mechanism. And the accepted reaction mechanism, the simplest mechanism that can explain the results, is a concerted mechanism, a one-step mechanism. That's the good news, only one step. The challenge is that when there's only one step, that means all of the bonds that are being formed and broken are doing so simultaneously. So we have a lot of curved arrows and a lot of partial bonds. Okay. So I've told you that the boron of BH2 is very Lewis acidic with that empty p orbital. And we know that alkenes are nucleophiles. The pi electrons of an alkene are nucleophilic. So it should not be surprising to know that this hydroboration reaction is initiated by attack of the pi electrons on that Lewis acidic boron. But we know that can't be all that's going on in the first step, because if that's all that was happening, what kind of intermediate would form? We'd form a carbocation. So we know we're not forming a carbocation. So before the carbon-boron bond forming is complete, we have attack of the sigma electrons in the boron-hydrogen bond on one of the carbons of our alkene. So that gives us a cyclic four-membered transition state that will look like this. Okay. So with the transition state, we've partially broken the carbon-carbon pi bond. We've partially broken the boron-hydrogen sigma bond. And then we've partially formed the carbon-boron sigma bond and the carbon-hydrogen sigma bond. As in our other additions, since we are breaking a pi bond and a sigma bond and forming two new sigma bonds, this process, this hydroboration, is going to be thermodynamically favored. Okay? So we progress from the transition state to the product, which is going to look like this. Okay? So how does this mechanism explain the fact that we end up with that we see syn addition only? Who would like to raise their hand and tell us how this explains the syn addition that is observed? Okay, Claire? Uh-huh. Yes, you're exactly right. It's a one-step process, and both groups are coming from the same molecule. And so the only way that both groups can come from the same molecule in one step is to come from the same side of the alkene. That's the only way that it will work. So that nicely explains the syn addition that is observed. Okay. So the other data we had was that we obtained the less substituted borane as opposed to the more substituted borane. How does this mechanism explain that? Yes, please. Okay, BH2 is bigger than hydrogen. So you'll have less steric hindrance in the transition state if BH2 is attaching to the less substituted carbon versus the more substituted carbon. Okay, so there's a steric explanation for getting the less substituted borane. There is also an electronic explanation, a little harder to see, a little more subtle, but this figure here shows us nicely the electronic explanation. I told you that the process is initiated by attack of the pi electrons on the boron. I told you that the boron-hydrogen bond attacks the carbon before that bond forming is complete, but the carbon-boron bond is more highly formed than the carbon-hydrogen bond at the transition state. So this sets up a situation where we end up with a partial negative charge on the boron, because bond making is more advanced at that boron than bond breaking is. And we end up with a partial positive charge on the carbon opposite the boron in the four-centered transition state, because at that carbon, the bond breaking is more advanced than the bond making, right? This is the third reaction now where we've seen bond breaking and bond making not occurring on the same time scale, but the bond making being initiated before the bond breaking is complete, okay? So we end up with the transition state, partial negative charge on the boron, partial positive charge on the carbon opposite the boron in that four-membered ring, four-center transition state. And we know that that partial positive charge is going to be more stable on the more substituted carbon. So this transition state is lower in energy than that transition state, both because of sterics and because of electronics. Question? Part of it is that if it held on to its hydrogen, you'd end up with a carbocation intermediate. And so the transfer of that hydrogen is facilitated by the fact that carbocation is going to be high in energy. As you start to develop a partial positive charge on that carbon, that entices that boron-hydrogen bond to attack that carbon. So borohydrides, or species that have a formal negative charge on boron, are fairly reactive, and we'll learn more about them in 352M. They do tend to transfer hydrogen. Okay, good question. All right, so both explanations, sterics and electronics, lead us to the same conclusion that the boron will attach to the less substituted carbon. Any questions about that? All right, so this figure shows us, and there's supposed to be bonds here that are left out somehow of this particular figure. The product of our hydroboration is an alkyl borane, and it has two remaining boron-hydrogen bonds that are capable of undergoing additional hydroboration reactions. So here we're just using ethylene, our simplest alkene, and you find that a BH3 molecule can hydroborate a total of 3 alkenes. So you could use 1/3 the amount of your BH3 in terms of molar ratio as you're using of your alkene in this reaction and get a good yield. Typically you use 1-to-1 because the reaction's faster that way, but you can use 3 equivalents of alkene to 1 equivalent of BH3. But the fact that alkyl boranes and dialkyl boranes are able to undergo hydroboration allows us to use bulky dialkyl boranes in hydroboration reactions. And this is useful because even though the less substituted alcohol is the major product, BH3 is fairly small, And so sometimes that ratio is not as favorable as we would like. So let's say we're getting maybe a 3-to-1 ratio of the less substituted to the more substituted product. But what we really want is like 20-to-1. That would be really, really useful. Well, the bulkier our borane species is, the more strongly we're going to favor the less substituted alcohol. So in the lab, if you're performing a hydroboration oxidation, many times you would use a dialkyl borane of this formula because that would more strongly favor the less substituted borane, which would give the less substituted alcohol. And there's one that's mentioned in the book. The abbreviation is 9-BBN. That stands for, I think it's 9-bora bicyclononane or some incredibly long name like that. I'm going to draw the structure for you. Let's see, it looks like something like this. And this is a boron up here. I think I've drawn that right. Let me just make sure. Yeah, let me make more of an angle here so it's a little easier to see. Okay. So you see we have a very, very bulky bicyclic alkyl group attached to that boron. So this molecule is going to give you probably 1% or less of the more substituted alcohol and would very reliably afford the less substituted alcohol in a hydroboration. Okay, so you'll see this used frequently in organic chemistry for hydroboration reactions. Any questions? Okay, let's talk about the oxidation. And as I mentioned, we'll just talk briefly about this because this is not the addition part of the reaction. So let's draw, we'll draw the borane that's up there on the middle board now. So we're going to react it with hydrogen peroxide and hydroxide, and it can be any of our hydroxides, but sodium hydroxide is convenient. And we're not going to learn the mechanism of this. It's a relatively complicated mechanism, so it's beyond the scope of what we're learning in this class. But what we will see is that it's a substitution. We're substituting oxygen for boron, but it's definitely not SN2 or SN1 because we have retention of the stereochemistry in this substitution reaction. The carbon-oxygen bond that forms has the same stereochemistry of the carbon-boron bond that is broken. Okay, so again, we won't go over the mechanism. A little bit complicated, involves some rearranging, but it's reliably going to give us retention, only retention of the stereochemistry. So when we combine a syn addition of hydrogen and BH2 with retention in the substitution, what we end up with is a net syn addition of hydrogen and OH to our double bond when we combine the hydroboration and the oxidation steps. Any questions? Okay, if you don't have any questions, then I have a question for you. So let's go ahead and get our eye clickers out. And we have a hydroboration oxidation. We've put a deuterium in this molecule just so that you can see stereochemistry in the products. And we showed you on Friday, this plus minus just means that each of these compounds is racemic. So go ahead, each of these compounds is formed as a one-to-one mixture with its enantiomer. So go ahead and talk to your neighbors and decide which of these compounds would be the major product from the hydroboration oxidation of this particular alkene. All right, let's try to get our final answers in the next 15 or 20 seconds. Okay, any more answers? Going once, going twice. All right, that looks like all the answers. Okay, so does the hydroboration oxidation give us the more substituted alcohol or the less substituted alcohol? Less. So which ones can we eliminate? Okay, A and B would be the more substituted alcohols, so we can eliminate those. And then we see what's the stereochemistry of this reaction? Syn. Okay, so which of C or D is formed by syn addition? Yeah, D is the one that has the hydrogen and the OH cis to each other. So D is the product of syn addition. That gives us the less substituted alcohol. Okay. So we see this is essentially the same problem we gave you as a sample problem in the book. It doesn't have the deuterium, which we just put in there to show you the stereochemistry on some of those answers. But what you see from this, the way they've drawn it out here, is that the BH3 is going to approach at equal rates from above and below the plane of this alkene. So that would give us a 1-to-1 mixture of enantiomers. And then when we replace the boron with OH by retention, then we have a 1-to-1 mixture of the enantiomers of the alcohol. Of course, if we had a stereocenter somewhere else in this alkene and one face was more hindered than another, then we wouldn't get a 1-to-1 mixture. We would get the hydroboration preferentially on the less hindered face, as we saw in an example earlier in the chapter when we were looking at hydrations. Okay. All right, so we have another summary table showing us what we've learned, summarizing what we've learned about hydroboration, oxidation, and we've given you a mechanism, a one-step concerted mechanism with carbon-boron bond formation being more advanced than carbon-hydrogen bond formation to explain these details, no rearrangements, syn addition, less substituted borane is formed. And then we didn't go over the mechanism for the oxidation step, but we taught you that it proceeds with retention of the configuration. So I mentioned this is a useful process, that it won H.C. Brown the Nobel Prize. One of many interesting uses of the reaction is shown here. So artemisinin is a very popular, very well-known anti-malarial drug. And one way to synthesize it requires this alcohol A. You see the carbons they've shown in red are showing up in this part of the molecule. They need the less substituted alcohol as opposed to the more substituted alcohol. So when they react this alkene in a hydration process, they need to do the hydroboration oxidation as opposed to the acid-promoted hydration that we learned earlier. Okay, so very, very useful process. Any questions? All right, so the last part of chapter 10 talks about organizing reactions and performing multi-step synthesis. And we're not going to go into great detail at this point. We're going to discuss it in these topics in more detail at the end of chapter 11, once we've added a few more reactions. But I will say that a multi-step synthesis or converting a starting material into a product in more than one step, not just a single step, is very important. It's important to know how to design a multi-step synthesis. And hopefully you're doing homework problems now that require you to do that, because those homework problems should have started to show up now. There's a process called retrosynthetic analysis that we'll talk a little more about on Friday. But it's working backwards from the product to the starting materials. And that's a very useful way of analyzing a multi-step synthesis problem. Our TAs this week in their recitations are going to go over some strategies for multi-step synthesis, and you'll see multi-step synthesis on the exam, and so it's important to be working those problems and practicing and talking to the TAs. There's just two things that we'll say in regards to multi-step synthesis at this point. The first one is that alcohols are readily available starting materials. Okay, you can obtain lots of alcohols from nature. Lots of alcohols are produced industrially, so you can open a chemical catalog and order a lot of different types of alcohols as starting materials if you're working in a lab. And so that means that many synthesis problems will require you to start with an alcohol. So it's very important to know how to transform an alcohol into various types of compounds. Those are the reactions we learned in chapter 9. Okay? And then the second thing that we'll tell you at this point is that alkenes are versatile intermediates. They're not quite as available from nature as alcohols, but we know how to make alkenes from alcohols. And we've learned a whole bunch of reactions in this chapter for making a lot of different compounds from alkenes. We can make vicinal halohydrins, which we can turn into epoxides. We can make vicinal dihalides, which we can turn into alkynes. We can make more substituted alcohols, less substituted alcohols, a whole bunch of things. So we can connect the reactions from chapter 9 with the reactions from chapter 10 in a multi-step synthesis, and there's a very good chance that you'll be asked to do so. Question? No, because there's more than one way to solve a synthesis problem, right? You could come up with a 10-step synthesis, but the likelihood is it'll be much less than that. The synthesis problems you'll see on exams shouldn't be too much more involved than the ones that you would see in the chapters, okay? But we can't put a number on it because there's going to be more than one right answer. Okay, so let's talk about alkynes now. And the alkynes chapter follows the alkenes chapter because there are a lot of similarities between alkynes and alkenes. They both have carbon-carbon pi bonds. Because of that, they both undergo addition reactions. So many of the reactions we're going to learn in chapter 11 will parallel reactions that we learned in chapter 10. So that'll help us. It shouldn't be as hard to master much of what we find in chapter 11. But there is something new. So first, let's teach you a little bit of vocabulary. If we have an alkyne at the end of the chain, then we have a hydrogen attached to an sp carbon, and that is called a terminal alkyne. Okay. In contrast, if we have the alkyne embedded within the chain and we have two alkyl groups attached and no hydrogens attached to our sp carbon, then that's referred to as an internal alkyne. Okay. So our terminal alkynes, based on the hybridization effect that we learned way back in chapter 2 when we were studying acid-base chemistry, our terminal alkynes are the most acidic hydrocarbons that we've learned about to date in the class. They're still very weak acids, but they're much stronger acids than alkenes or alkanes. They're strong enough acids that we can take a really strong base, and we'll talk about which bases in this chapter, and deprotonate a terminal alkyne. And that gives us a really strong nucleophile, and we can use that really strong nucleophile in SN2 reactions. And that's valuable because that's going to allow us to make longer chains. If we react it with an alkyl halide, we can make a longer chain from smaller building blocks, okay? And that's something you're often asked to do in synthesis problems. Question? Stronger, it makes a more stable conjugate base, and so therefore it's a stronger acid. Okay. All right, so that's the new chemistry we're going to learn in this chapter. is the formation of the conjugate base of a terminal alkyne, and then using that as a nucleophile in SN2 reactions. But in addition to that, we're going to learn addition reactions that parallel the addition reactions we've learned in chapter 10. Before we get into that, let's just take a look at the structures of alkynes. Let's open up figures from chapter 11. And the first one we see is one showing the orbitals that are involved in the carbon-carbon bonds of alkynes. So we have sp hybrid orbitals that overlap end to end and form the sigma bond between the two carbons. And then we have two p orbitals on each carbon that are orthogonal to each other. They're perfectly perpendicular to each other, so they don't overlap at all with each other, but they overlap nicely with p orbitals on the adjacent sp carbon, giving us two pi bonds that are totally orthogonal to each other in perpendicular planes, and that's the structure of our alkyne. So another interesting feature of our alkyne is noted when we look at bond dissociation energies. Okay. So the bond dissociation energy for acetylene, this is the amount of energy it takes to completely cleave the carbon-carbon bonds in acetylene, is pretty high, as you might imagine, since there's 3 of those bonds, 200 kcals per mole. We can compare that to the bond dissociation energy of ethylene, and that value is 152 kcals per mole. So we subtract, and we find that the bond dissociation energy of acetylene is 48 kcals per mole higher than that of ethylene. We would expect it to be higher because the triple bond is stronger than the double bond. However, earlier in the class, we did a similar comparison with ethylene and ethane. Ethane is carbon-carbon bond, and ethane is, I think it's 88. And so the difference between ethylene and ethane was about 64 kcals per mole, significantly less, or more, sorry, than the difference between ethylene and acetylene, okay? So what we can conclude from that is that the pi bonds in acetylene are not as strong as the pi bonds in ethylene, okay? So acetylene would be more reactive in addition reactions than ethylene would, okay? And another conclusion we can make, the pi electrons in acetylene are more loosely held than the pi electrons of ethylene. So which would you expect to be more polarizable, ethylene or acetylene? Okay, which was? Acetylene, yep. We have a smaller difference in bond dissociation energy between acetylene and ethylene, telling us the pi bonds in acetylene are not quite as strong as the pi bonds in ethylene. Those pi electrons are not held as tightly. So we would say that acetylene is more polarizable, meaning that its pi electrons are going to adjust more readily to their environment than the pi electrons of ethylene will. Question?
Do we know why that is?
Somebody probably does, but I must confess I'm not the one who can answer that. That would require a deeper understanding of physical chemistry than I have. But the answer would lie in physical chemistry theories. So for now, we're just learning it in connection with the fact that acetylene is going to be more polarizable because those pi electrons are not as tightly held. Okay. All right, we'll go ahead and stop there. We'll briefly cover some nomenclature of alkynes, and then we'll dive more deeply into their chemistry.